Have you ever looked up at the night sky, filled with countless stars, and wondered what it all is? It's a vast, beautiful, and deeply mysterious place. We see galaxies spinning in the dark, planets orbiting distant suns, and nebulae where new stars are born. For thousands of years we have told stories to make sense of this cosmic ocean, and built powerful telescopes to peer deeper into the void. Yet for all our knowledge, the universe continues to hold its greatest secrets close. The more we learn, the more questions we find ourselves asking. We have a widely accepted theory, the Big Bang, which suggests that everything we see today began from a single, incredibly hot and dense point nearly 14 billion years ago. To understand this wild idea, we first need to get to grips with what a black hole is. A black hole is a region of space-time where gravity is so incredibly strong that nothing, not even light, can get away. Imagine throwing a ball up into the air. It goes up, slows down, and then gravity pulls it back down. Now imagine throwing it so hard that it escapes Earth's gravity and flies off into space. A black hole's gravity is so immense that its escape velocity is faster than the speed of light. These cosmic monsters are formed when a massive star, many times larger than our sun, reaches the end of its life. The star runs out of fuel and collapses under the weight of its own gravity. This collapse is so violent and complete that it crushes the star's core down into an infinitely small and dense point called a singularity. Every black hole is shrouded by an invisible boundary known as the event horizon. This isn't a physical surface you could touch, but rather a conceptual line drawn in space. It's the ultimate point of no return. Imagine you're in a boat on a river that's flowing towards a massive, infinitely tall waterfall. Far from the falls, the current is gentle, and you can easily paddle your boat upstream, away from the danger. At some point, you cross an invisible line where the river's current is flowing faster than you could ever possibly paddle. From the perspective of a distant observer, something very strange happens to an object falling towards a black hole. As it approaches the event horizon, it appears to slow down. Its light gets stretched to longer, redder wavelengths. It would seem to just hover at the edge of the black hole, getting dimmer and redder over an infinite amount of time, but never quite crossing. The man who first gave us the tools to understand these bizarre phenomena was Albert Einstein. His theory of general relativity, published in 1915, completely revolutionized our understanding of gravity. He asked us to imagine space and time woven together into a single four-dimensional fabric, space-time. Massive objects create dips or curves in this fabric. Smaller objects, like planets or light rays, just follow the straightest possible path through this curved space-time. A planet orbiting a star is like a marble rolling around the edge of a funnel. The first exact solution to Einstein's equations that described a black hole was found by Carl Schwarzschild in 1916, while he was serving on the front lines of World War I. His mathematics described a non-rotating, uncharged black hole with a singularity at its center and an event horizon at a specific distance, now called the Schwarzschild radius. Now we arrive at the heart of this incredible idea. We have the Big Bang, our universe's explosive beginning from a point of immense density, and we have black holes, cosmic objects that end in a point of immense density called a singularity. On the surface, they seem like opposites. But what if they are two sides of the same coin? This is the core of the theory that our universe might be nestled safely inside a black hole. This isn't just a random guess. It's a possibility that emerges when scientists try to merge our two best theories of the universe, general relativity and quantum mechanics. At the singularity of a black hole, or at the moment of the Big Bang, you have a huge amount of mass and energy crammed into a tiny, quantum-sized space. Instead, they propose that when matter gets squeezed to an unimaginable degree, new quantum effects kick in. These effects could resist the crush of gravity, preventing the formation of a true singularity. This quantum pushback could cause the collapsing matter to rebound violently. This bounce, according to the theory, would look just like a Big Bang from the inside. If our universe is inside a black hole, where is the edge? The answer is both simple and mind-boggling. We can't ever reach it. According to the theory, the boundary of our universe, the cosmic horizon that we cannot see beyond, is essentially the event horizon of the black hole we live in. As our universe expands, we're We're constantly moving away from this boundary. The event horizon is a one-way membrane. Information can get in, but it can't get out. We are fundamentally isolated, cocooned within our own private bubble of space-time. This makes the theory very difficult to test directly, as we are permanently cut off from any evidence of the world outside. Some scientists have suggested that if our universe was born this way, there might be subtle, large-scale patterns left over from the collapse and bounce. Searching for such subtle alignments or anisotropies in the cosmic microwave background, or the distribution of galaxies, is one of the few potential ways we might find a hint of our cosmic origins. For now, however, our universe hides its secrets well. Once we entertain the idea that our universe could be born from a black hole, a breathtaking possibility immediately opens up. If it happened for our universe, why couldn't it happen for others? In fact, our own universe is filled with black holes. If every black hole has the potential to create a new universe inside it, then the cosmos could be teeming with worlds beyond our own, each one a separate bubble of space-time. This leads us to the concept of the multiverse. Parent universes give birth to child universes through black holes. These child universes then grow, evolve, form their own stars and galaxies, and eventually their own black holes. These black holes, in turn, can become the gateways for a new generation of grandchild universes. In this grand vision, black holes are transformed from cosmic destroyers into cosmic creators. They're no longer just the end point of matter, a gravitational abyss from which nothing escapes. Instead, they become gateways, portals to new beginnings. The one-way membrane of the event horizon, which seems so final from the outside, is actually the protective wall of a cosmic nursery. If we are part of a cosmic family tree, what does that say about our own universe's heritage? The properties of our universe, its fundamental constants, its rate of expansion, the amount of dark matter and dark energy, might be inherited traits passed down from our parent universe. The slight variations that might occur during the collapse and rebound process would allow for cosmic evolution, with each new universe being a little different from its parent. This perspective offers a solution to the fine-tuning problem. Scientists have long been puzzled by the fact that many fundamental constants of nature seem to be exquisitely balanced to allow for the existence of complex structures like stars, planets, and life. The black hole multiverse theory suggests this isn't a miracle. We simply live in one of the universes that, through generations of cosmic natural selection, evolved to have the right combination of traits to be stable and produce us. This also means that our universe may have cosmic siblings, other universes that were born from different black holes within the same parent cosmos. Ultimately, this theory places humanity within a grand evolutionary story that extends far beyond our own Big Bang. Our universe is not a standalone creation, but a link in an ancient and ongoing chain of being. We are the inhabitants of one branch on an infinite tree of worlds, a product of physical laws that favor reproduction and complexity. We have journeyed to the edge of reality and back, exploring a theory that is as profound as it is mind-bending. The idea that our entire universe, with its billions of brilliant galaxies, might exist inside a black hole is a testament to human curiosity. It takes two of the most mysterious concepts in science, the origin of our cosmos and the nature of black holes, and weaves them together into a single, elegant, and startling narrative. This is not just a fanciful story. It is a possibility born from the rigorous mathematics of our best physical theories, a signpost pointing towards a deeper, more interconnected reality than we ever imagined. Whether this theory ultimately proves to be correct is not the most important point. Its true value lies in the way it pushes our intellectual boundaries. So the next time you look up at the night sky, allow yourself to wonder, could that vast expanse be contained within something else entirely? Are the black holes scattered among the stars not just endings, but the seeds of new beginnings? We may not have the final answers today, but the act of asking these immense questions is what propels us forward. It is what fuels our telescopes, our particle accelerators, and our deepest thoughts. The quest for knowledge is a journey without a final destination, and the beauty lies in the exploration itself, in the humbling and exhilarating process of discovery. And as long as we keep asking, we will keep discovering, forever expanding the horizons of our cosmic home.